Hello everyone. So today we are going to discuss planetary motion. This is the main important portion in this chapter, planetary motion. And here we are going to find the orbit for the gravitational interaction between planets in solar system, or the orbit of the planet. And the interaction is mainly between planet and the sun. Okay. So we have the gravitational interaction. We have the gravitational interaction U of r is minus gmm by r, and we have taken c as a constant is equal to minus gmm. And what is m? Capital M is the mass of sun, and small m is the mass of the planet. And in this situation, and here we have to remember some points, and that is, if both bodies were homogeneous spheres, we can consider their interaction as point, or the bodies like point particle. That is, if the bodies, that is the planet and also the sun, were homogeneous spheres, perfectly homogeneous spheres, there is no mass concentration in the planet. That means homogeneous in all the way, and they are perfectly spheres. We can solve for orbit, for the equation of orbit, by taking them as point particle. And most of the members of the solar system are neither homogeneous, or neither perfect homogeneous nor perfect spheres. But the actual case is that most of the members in the solar system are not homogeneous spheres. Okay, not homogeneous system, and also not perfectly spheres. We can have some examples. We can consider satellites around the moon, and the satellites were perturbed, or the path of the satellite is perturbed due to the mass concentration in the moon. We know that there are a lot of mass concentration, in n number of mass concentrations in moon, so that this mass concentration will perturb the satellite. So this is the one point we have to remember. These are not homogeneous spheres. Satellites, planets, and the bodies in the solar system are not homogeneous. This is one example for that. And solar system, this solar system is not a two-body system. We cannot consider solar system as a two-body system. If we are considering two bodies like two planets, or one planet and one solar system, if we are dealing with this situation, it is not just a two-body system. There are n number of planets, there are so many planets and other bodies in the solar system. So it is not a two-body system actually. So this is actually there are so many interactions between the bodies. Not only the interaction between the considered planet and the sun, there are so many other planets interacting with all these planets each other. So this is one situation to explain the solar system is not homogeneous, and the bodies in the solar system is not homogeneous. So another example, we can see that the planet Mercury may be slightly perturbed by an equatorial bulge of sun. That is, the sun is not actually a sphere, so the equatorial bulge of the sun may cause perturbation in the planet Mercury. So these are the points that we have to remember when we are dealing with the planetary motion. And one thing, it is unfortunately none of these effects is particularly large. So most of the mass of the solar system is in the sun, so that the attraction of the planets for each other is quite feeble. So this is a fortunate case, that is the interaction between the other planets with the planet that we are considering is not a much large interaction, because the massive body in the solar system is the large mass is concentrated on in the sun. So these other interactions are quite feeble. It's very much less or can be neglected. So in the solar system, the largest interaction is of Jupiter and Saturn, and these two, the interaction between Jupiter and Saturn is the largest interaction in the solar system is between Jupiter and Saturn, and this interaction may cause it will change the speed of each planet. It will change the speed of each planet, and in this case the law of equal areas no longer hold exactly. Actually, every planet in the so we will study in the Kepler's laws. There is a mentioned it in the general properties of central force, that is in each in the orbit they sweep equal areas in equal in a particular time, or per second they sweep equal areas, and in this case it will the perturbation due to this interaction, the interaction of Jupiter and Saturn will in this case the law of equal areas is not held exactly. So these are the things that we have to remember. And returning to our calculation to find the orbit of the planets, or we have to calculate, or we are dealing with the motion of planets. So for the calculation, firstly we have to calculate the planetary orbits neglecting other planets. So we are calculating the planetary orbits and neglecting all other interactions between other planets. When you are considering one planet, we will neglect all the interactions with the other planets. Okay. And the second step is to calculate small corrections to the orbit due to their presence. So we will eliminate, or we will correct the orbits, the equation of orbit. We will correct the equation of orbits due to the presence of other planets. That's the second thing we are doing in this calculation. So firstly we will calculate for finding the motion of the planets. Firstly we calculate the planetary orbits. So we will find an equation for orbit, and here we were neglecting the most of the interactions with other planets. Also we will second step we will eliminate, or we will correct the equation of orbit, and if there is any term is there in connection with the presence of other planets. And that in the third step, if the body is not quite homogeneous or spherically symmetric, its gravitational field can be shown to have terms depending on 1 by r cube, 1 by r raised to 4, etc., addition to 1 by r square. So as I said earlier, and in the third step, if the body is not quite homogeneous or spherically symmetric, its gravitational field, we know that the gravitational field is directly proportional to 1 by r square. If the planets are not homogeneous or spherically symmetric, there will be this term can be erased due to this homogeneity addition to r 1 by r square. So this term can be neglected over the span of solar system, since the mass mainly concentrated on the sun. So for idealized planetary motion, we have the gravitational potential U of r is equal to minus E by r, where C is equal to minus GMM. We have already have the equation for the orbit. In the last session, we have the equation d theta by dr is equal to L by 2 mr square into 1 by root of 2 by mu E minus u effective. Just refer that equation, and on integration you have to integrate to find the values in terms of r. So integrating and rearranging all this, and you have here we will substitute the values for u effective, and u effective is equal to L square by 2 mu r square plus u of r. Substitute all this and integrate, you will get theta minus theta 0 here. D theta, put this d theta in this side, and let the dr to this side. So theta minus theta 0 is the constant of integration. On integrating d theta, you will get theta, and you have theta 0 as the constant of integration. Theta minus theta 0 is equal to L into integral of, and we have to integrate this term, and this term is from when you substitute u effective and rearrange this term, you will get this term, and the result will become, and I just write the result of this integration. You do this integration, and you will get sin inverse mu cr minus L square divided by r into root m square c square plus 2 mu E L square. Or you can rearrange this term, you will get it like this. This is sin inverse, and you put the sin inverse here, you will get sin theta minus theta 0, and rearrange, and you will get an equation like this. You do it yourself, and solving for r from this equation, you will get r is equal to L square by mc divided by 1 minus root of 1 plus 2 E L square by mu c square sin theta minus theta 0. And usually, conventionally, we are taking theta 0 is equal to minus pi by 2, and you will get r0 is equal to, and also you put r0 is equal to L square by mu c. Just put r0 for L square by mu c, and mu is the reduced mass, and epsilon is equal to root of 1 plus 2 E L square by mu c square. Just put epsilon for this term, and epsilon is known as the eccentricity, and it will this epsilon will characterize the shape of the orbit, and the orbit will change according to the value of the epsilon, and this epsilon is known as eccentricity. So your equation will become it will become more compact in form. So r is equal to r0 1 minus epsilon cos theta. It is sin theta minus pi by theta plus pi by 2. It will become cos theta, and the equation will become like this. And it is more comfortable to use Cartesian coordinate system. So put x is equal to r cos theta and y is equal to r sin theta, and the equation will become r minus r cos theta is equal to r0. This equation will become r into 1 minus epsilon cos theta is equal to r0. This equal to r minus r epsilon cos theta is equal to r0, and what is r? R is x square plus y square whole raised to half minus epsilon x is equal to r0. And you do this calculation, and you will get like this. r0 square is equal to, just remove this square root and you will get an equation for r0 square, and it is equal to r0 square is equal to 1 minus epsilon square x square minus 2 r0 epsilon x plus y square. So this is the equation for r0 square, and these are the possibilities to become these are the possibilities for the motion of the planet in an orbit. So the value of x, as I already said, the value of eccentricity epsilon will give you the shape of the orbit that a planet is revolving. So when epsilon is greater than 1, look at this equation. When epsilon is greater than 1, this equation will become minus x square, some value, minus value, this will become negative, and some negative value into x square, plus this term will be plus y square. So the coefficients of x square and the coefficient of y square are unequal. It will become unequal and opposite sign. It will minus x square and here it is plus y square. So it is in opposite sign and their coefficients are unequal. So the equation has of the form y square minus ax square. This is the term 1 minus epsilon square. It will and put it as a and this term as b. So it will become, is of the form y square minus ax square minus bx is a constant. This is an equation for hyperbola. So you have the value of epsilon is equal to 1 plus 2 e l square by mu c square, and when epsilon is greater than 1, this e must be positive. So its possibility is greater than 0. For this value epsilon is greater than 1, and this is the equation for hyperbola. So this is the condition for an hyperbolic orbit. In the second case, epsilon is equal to 1, this equation will become r0 square is equal to, this will go to 0, it will become, it is epsilon is equal to minus 1 to r0 x plus y square. So rearranging, you will get x is equal to minus r0 by 2 plus y square by 2 r0, and this is an equation for hyperbola. When we get epsilon is equal to 1, only if E is equal to 0. Epsilon is equal to 1 when E is equal to 0. So the energy is equal to 0, epsilon is equal to 1. So this is the equation, this is the epsilon value for E is equal to 0, and this is an equation for parabola. So when this condition attains, the planet will go around a parabola. So the orbit of the planet will be parabolic in shape. So the third case, 0 less than or is equal to epsilon less than or is equal to 1. So epsilon is less than 1 and equal to or greater than 0. The coefficient of x square and y square are unequal but have same sign. So look at this equation. When epsilon is less than 1 and greater than 0 is equal to or greater than 0, this will be a positive quantity. So the coefficient of x square and y square will be positive in sign, but their coefficients, magnitude of the coefficients are unequal. So the equation will be of the form y square plus a square minus bx is equal to constant, and this is an equation for ellipse. So when this condition attains, the planet and the planets which satisfy this condition will go through an ellipse, and its orbit will be in elliptical in shape. So the condition for E less than 1 is minus mu 0 square by 2L square is less than or equal to E less than or equal to 0. You look at this equation for epsilon. You put the values, put the condition for epsilon less than 1. You will get minus mu c square by 2L square less than or equal to E less than or equal to 0. Then only epsilon less than 1. Epsilon will become less than 1. So when E is equal to minus mu 0 square by 2L square, epsilon is equal to, when E is equal to minus mu c square by 2L square, epsilon will be equal to 0, and the equation will become epsilon will be equal to 0. So this term will go and A is equal to 1. So the equation will become x square plus y square is equal to r square, and this is an equation for circle. So the when this condition satisfied, when the condition satisfies, the planet will revolve around the circle. Okay, so the orbit of the orbital circular in shape. So ellipse will degenerate to a circle in this case. So we will discuss more detail. We will discuss hyperbolic orbits in more detail in the next session. So this is about planetary motion.